Hello grade 10s, my name is John and I'm here to work with you and go through with you the important topic of the microscopic view of matter. Now you might be wondering, well, we know a little bit about matter. We know that it exists as solid, liquids and gases, but what's really inside matter? Let's take off put on some glasses and let's get right down into what matter consists of. That's what we're going to be doing today. So let's have a look at the important features or the important concepts that we're going to be focusing on. Here we go. A microscopic view of matter. It's not even microscopic. It's smaller than microscopic, but we call it microscopic anyway. So what we're going to start by looking at is some pure substances, and the most simplest pure substance is an element, and we arrange elements on the periodic table. We'll have some overview about that. Then we're going to say, well, what are elements made up of? And there's been this idea that's been around for a very long time, going back as far as the ancient Greeks. They thought that there were tiny little particles that matter is made up of, and they called the smallest particle the atmos, and that's where we get the word atom. Through years and over time, models and people's thinking about atom has changed. And that's what we're going to be taking a look at today. So we're going to be looking at different models of the atom because we can't really see it. So we've got to get a picture, an idea of it. And what we'll then do is, having defined what our modern views, or one of the modern views of the atom, we're going to be taking a look at what we understand and what you need to know about the structure of an atom. We're going to look at the nucleus. We're going to look at electrons. We're going to look at, very briefly, how some of these atoms join together. Because you see, atoms are the building blocks for matter. So if we want to go back to a little while, you might recognize we have a whole lot of pieces of Lego, but we need to fit them together in different ways. And that's what atoms do. We combine atoms and they form bigger things, bigger structures, bigger particles. And we're going to be looking at some of those bigger particles, and then we're going to represent those things as they form compounds. We'll talk about representing compounds. So there's quite a lot that we've got to go through, starting with the elements periodic table, which we'll refer to all the time, looking at the models of the atom, and then finally developing the idea of what's really inside compounds as well as what's really inside elements. Okay, so where are we going to start? Well, let's have a look at some common materials, stuff that you might find around your home even. And I'd like you to take a macroscopic view of them. I've got some things here on the desk, and I would just like you to have a look at it. So let's get the camera on there and have a look over here. What I've got in my hand is a piece of aluminium foil, and you can see it's shiny and it's quite solid because I've wrapped it really nice and tight, but it has a very different appearance to this copper wire. If I had to unwrap this ball of aluminium, we would recognize that it would be in a foil. It's in a thin sheet. And it's still not tearing. It's still quite strong. I can pull on it, and it's doing quite fine. Whereas this copper wire, different color, and I've just got a whole lot here so you can see it. I hope it's clear. You can see it's this orangey color, and it forms in thin strands. Now, those are the macroscopic properties of metals. I've also got a piece of lead here. It's much stronger. It's very hard to bend, and it's quite heavy. The lead here, which comes from a balancing weight that you have on your tire, what's it made up of? We have to get right inside the aluminium or the copper or the lead. What would we find? Here's another piece of solid that you might be familiar with. It's a piece of ice. Starting to melt here. Water is changing from its solid phase into its liquid phase, and you can perhaps even see that's happening as we're watching it. But what's inside there? what are the particles? What's the macroscopic view of this stuff? And then I've got something else here that looks quite interesting. A black lump of stuff. This is basically carbon. What's inside it? We know that carbon comes in different forms. It comes as a diamond as well as charcoal. But here's carbon that I've actually got when I've taken all the water out of sugar, and I'm left with a solid lump of carbon. And here's something else that's quite interesting. It's very pretty, very nice color. I'm just going to take it out and put it on my hand. It's some copper chloride. And if we can get in really close, you'll be able to see the copper chloride's made up of tiny, tiny little lumps, little crystalline particles. They're shining in the light, and under a magnifying glass, they'll have a particular shape, and we'll be able to look at those. Now, all of these are different forms of matter, but what's on the inside? Well, let's start with the simplest form of matter. And you will remember that we've spoken about elements as a pure substance, that it can't be made any simpler. And so what scientists have done over time, and they've taken quite a long time to do it, is they've started to collect the properties of elements, because elements aren't found very easily in nature. There are a few elements like gold that you can find. Those are not reactive, but most elements are reactive. Even oxygen, which is an element that's combined and forms a particular substance, a gas. But we've got things like helium, which is an element and exists in the atmosphere. Not very common to find it. But these elements, as I said, have different properties, and people have grouped them together into a formation which we call the periodic table. So let's just define the element, as we've said over here. An element is a substance, and it's a pure substance. Very important that we understand. When we say pure, remember that means that all the particles, all the substance, if we break it in half, it's going to be exactly the same. It can't be broken down into other substance through chemical means. When we talk about chemical means there, we're talking about using electricity, we're talking about heating, we're talking about those particular processes that simplify and break things apart. Can't break elements apart. They remain the same. Even the smallest amount will have the same properties as a bigger quantity. So if we take copper, for example, even if we got a really small piece of copper, it would still have the characteristic orange color, unless we got right down to a very tiny nanotechnology scale, and then the colors might change a little bit. But basically, we'd say that even small things that we can make little particles of, they're pure, they're copper, they have the properties of the element. Now, what scientists have done, and it's gone over for a long time, a very famous man called Dmitri Mendeleev was at the beginning of the modern era of chemistry. Dmitri Mendeleev was the father of chemistry in many respects. And what he did is he started to look at these elements, started to classify them, put things that have similar properties together in an order. And so he started to notice that there were some things that behaved in the same way and some things that behaved differently. Put them into a particular arrangement that we now know as the periodic table. So have a look at this, and we'll just highlight some of the features of the periodic table. The periodic table arranges the elements to show similarities and differences in the physical and chemical properties of the elements. The interesting thing about Dmitri was that Father Dmitri, he actually predicted, even though silicon or gallium, germanium weren't discovered at the time, he predicted what their properties were before the people actually found them. And he said, this is how you'll find them, this is what the properties will be. So because of the periodic nature, periodic means it repeats, periodic, it's a repeatable pattern, it's a pattern, repeats. And so there are properties and there are ways of arranging. And I want to just highlight some of those ideas here. The first thing you'll notice is that there are columns, or what we will call, that's a column. We give them numbers. Each of these columns is given numbers. Although this looks a strange arrangement, each of these columns is given a number. That's called a group. Okay, so the group number here is number 1. This is in the second column, so it's group 2. And this one would be group 3, group 4, and so on. And we'd get to group 10 over there. And there we get to group 13, 14, 15, 16, 17. There are 18 groups altogether. Now, that might seem a little strange, but it's a reason that we've got it, is that's the way it is. People have discovered there are trends, there are patterns to follow. And so we've put things that have similar properties in the same group. I'd like you just to have a look at what these elements look like. There are only a limited number of elements found in nature, and I'm going to show you a picture of them. Here's a website that's periodictable.com, and it gives you photographs of each of the elements, and you can see they all look a little bit shiny. Here are the metals, and if I go across onto the other side here, because I need to, what you'll notice here is they start to change. Here we've got a yellow one, and here we're starting to get gases, and look at all of those. Those look very similar. They seem to all be related to lighting systems where they've got helium, neon, argon, krypton, and xenon. They're all lights, and you can see that they are all together in the same group. Whereas something like on the other side here, if we take a look at lithium, sodium, potassium, you'll see that these ones, for example, this is lithium. It's a nice solid metal. It's a shiny silvery color, and we've got a good picture of it there to recognize. Right, now the other thing that you'll notice is that on the periodic table that we've not only got columns, and there are all these columns. Some of the groups have special names, and we'll mention those a little later, but they're also found in rows, and I want to indicate those rows to you over here. There's a row, okay, in my orange color. This is known as a period. So we have groups that go up and down, and periods that go from left to right. And what happens is we'll notice if we start on the left-hand side, lithium is over here, then we get beryllium, then we get boron, carbon, nitrogen, oxygen, fluorine, neon. What happens is we go from left to right, there is a change in the characteristics. So across a period, you get a change. You get a pattern. And guess what? What we've seen in period 2 repeats itself in period 3. And that's why it's known as the periodic table. Now, what's really important for us to recognize is, yes, we've spoken about the periodic table, arranging things according to their groups, but in today, and their periods, but today what we're wanting to do is saying, hang on guys, we see this macroscopic picture of something like lithium, but what's inside it? Well, here's the good news. Inside every element, there are atoms of those elements. And so that's the important point that I want to make to you today, is that inside an element, the smallest unit of any element is the atom. The atom is the building block of not only elements, but obviously we'll see that later elements can join together to form bigger structures. So when we start at the very smallest particle, we're dealing with the atom. So what do people think the atom is made up of? How can we find out about the atom? Can we dive down, get a powerful microscope and look inside the lump of carbon and see what's happening inside? Unfortunately, it's too small. The atom is very, very small. We can't even measure it. So you say, but how do we know what's there? Well, that's where there's some very clever people have come up with some ideas over a period of time. And so when we're not sure of something, what people start to do is they start to think about ideas. They start to build an idea in their head, which is a model. A model isn't the real thing. If you are into model building, you can get models of a jumbo jet, and you can put them together. It's not a jumbo jet. It just looks like a jumbo jet, just smaller than the real thing. Now what we're doing, we're going the other way. We're saying we want to understand what something very, very small is. So what we'll do is we'll have a model that represents it, that explains the properties, that explains why things behave the way they do. So what we need to recognize is that we've got two views here. We've got a very small view, the macroscopic view, but we've got the big view. The macroscopic view is the big view, the small view is the microscopic view, and the model is the link between those two. What's really happening? We're going to represent that in a picture, an idea. And so we go back all the way to the beginning of the 1800s, and we come to different people's ideas of the atom. We'll start with this particular one, and the man that we're dealing with here, his name was John Dalton. And John Dalton said, after doing lots of experiments, he said, look, from my experiments, it's very important that we understand this, that matter is made of small particles, tiny particles, small particles. And he recognized and said, they're all the same, you can't divide them, they're not divisible, you can't divide, not dividable, divisible, you can't divide, and they're all the same. They have different masses, but what we recognize is that they're all solid spherical things, indestructible. And so that was Dalton's picture of an atom. It didn't take a very long, and people started to accept, well, yeah, Dalton, you've got a good idea. You can explain what's happening in real chemistry when you use your model of the atom. We can explain chemical reactions by recognizing that these indivisible small particles, which became known as atoms, can join together to form substances. And so Dalton was the first one that really started this journey of indivisible solid spheres that you can't break apart. They have different sizes, they have different masses. But along came the next man. His name was J.J. Thompson, and his model looked quite different to Dalton's. The reason for this is that between Thompson and Dalton, there were some important discoveries. The discovery of theory about electricity and the use of electricity. Now, you might all know that if you rub your ruler on your jersey, you can get an electrostatic charge. So how could we explain these electrostatic charges that were taking place? Well, with Dalton's model, you couldn't. With Thomson's model, people started to say, but where did the charges come from? And that's where Thomson's model started to do some explanation. I want you to have a careful look at what his model included. It was known as the plum pudding model. Now that's a very old-fashioned term, and not many of us have plum puddings now. But basically what it is here's like a solid cake. And on the surface of the cake, he said that there were smaller particles. Some of them were positive, and some of them were negative. And as you take your ruler, he said, imagine this. You've got a whole lot of these things next to each other, and as you take your ruler, you can either rub off a negative or rub off a positive. These are like raisins or plums in the pudding that can peel off from the cake. So this was different stuff. These were different. This was a different solid stuff. This is still solid, but this is the negative particle and that's the positive particle. And they could be rubbed off. But the atom itself, he still thought inside the atom you couldn't really break it apart. But then there was the next man who came along and said, but hold on, we've had some more discoveries since Thompson. They've discovered, Madame Curie came along and she discovered radioactivity, which found that there were little particles coming out of substances that had very high energy. And so the next guy that we're going to talk about, his name was Rutherford. And Rutherford said, well, let's use some of these particles that are radioactive particles and see if we can bomb into an atom. So he got a very thin piece of gold and he bombed into an atom. It's a very famous experiment known as the Rutherford gold foil experiment. And what he found was that these little particles were going, that he had got going from a radioactive source. Here he had his gold foil. And if we had this model, if we had Thompson's model, what would you expect? Well, you've got a solid barrier here, a little particle. Is it going to get through or not? Well, the expectation was that most of the particles would be rebounded, would reflect off the solid particle. But it didn't happen. Most of the particles actually went straight through. Surprise, surprise. How are we going to explain this? Rutherford said. Well, there was some other interesting stuff that happened. Here was something else that was quite interesting. Some of the particles, instead of going straight through, they went on a curve. Some of them went that way. And the thing about these particles, these were positively charged particles. So when they did some maths calculations, they recognized that this deflection was caused between this particle moving, positive moving, close to another particle. What do two positives do? A positive and a positive will repel each other. Now the fixed particle, the one in the gold foil, can't move. The other one bends away. And so that's exactly what Thompson, or Rutherford at least, began to see. That what we've got here is a very different picture of the atom. And I want to show you his picture of the atom, which has become almost a symbol of the atom over time. Here it is. He said, it's not drawn to scale, and that's a very important thing to notice, that in the center of the atom, there is a very small center. And what we call that center is the nucleus. It has most of the mass. And what he recognized is that on the outside of the nucleus, there were these negative particles. And because we needed to give them a name, he called them electrons. He said these electrons are moving in orbits around the nucleus. But between here, between the center and where the electron is, what's in the middle? He said this is empty space. Doesn't exist, doesn't have anything filling it. It's not matter. It's just empty space. These electrons are moving so quickly, and they're all the time moving, that they're taking up the space and filling that. And that's why atoms are still overall solid. Kind of a confusing idea, but it seemed to make sense at the time. And so that's where we're going to start with our picture of the atom, when we say, let's go into a little bit more detail about what's happening inside the atom. So let's have a look at the atomic structure of the atom as we know today. Based on these principal models, Dalton to Thompson to Rutherford. They're all based on experimental results. Please remember that. And it's not that science is static. It illustrates to us that when new evidence comes forward, we've got to change our ideas. We've got to introduce a new idea that becomes a new model or a new theory that replaces the old. So let's think about what we need to know from these models. So the first thing that we're going to look at is, yes, the nucleus. And as I've said to you, this is where the mass is. Okay? And what we have in the nucleus, what we now know, is that we have some positive particles. So these are called protons, and we give a symbol P+ to them. But we also begin to recognize, after some time, another scientist by the name of Chadwick came along, and he said, you know what, the nucleus also has some neutral particles. So these neutral particles are they're neutral. They don't have a positive or a negative charge. They're neutral. They're called neutrons. And together, these two particles make up the nucleus. And we can sometimes even call them nucleons. Nucleons. Because they live in the nucleus. Now, to give you an idea, this nucleus has Very, very small mass. It's tiny, tiny, tiny. You haven't even got a scale big enough to measure it. If we had to put it into grams, it's times 10 to the minus 36 or somewhere around there, kilograms. Very, 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 very small. That means 0,000 for 36, and then you get to a number. So understand that it's very, very small. A very small mass, and in fact, the particles are very small. Now, what we need to recognize from that is that every atom is different as well. And this is the important thing that we need to take note of now. That in the nucleus, the number of protons isn't the same. The number of protons for different atoms differs. And so what we have here is something called the atomic number. And the atomic number is equal to the number of protons. And this is what gives the elements their specific properties. The size and the mass and the charge of the nucleus. Now remember that if we've got a proton here, the atom overall is neutral. The atom can't just be positively charged. It's not an atom then, it's something else. But what we recognize is that for every proton, there's an electron. For the moment, we're focusing on the proton, on the nucleus. So we'll say the atomic number tells us how many protons there are. Sometimes elements can lose electrons. That's why we don't have the number of electrons are always equal to protons. For an atom, we say the number of protons tells us what atom it is. So let me give you an example of that. And this helps us understand the periodic table as well. I'll just go to some blank space here. If we take a look at hydrogen, which is the smallest, it's a very light gas, it's a low density, and what we recognize, the hydrogen atom has only got one proton. And therefore, the hydrogen atom will have one electron as well. It's tiny. So we'd say that it has an atomic number, Z, the atomic number equal to 1. If we take a look at the next element on the periodic table, it is helium. And helium, it has 2 protons. And it also has 2 electrons. It has an atomic number equal to 2. So if we get to lithium now, which is the next one on the periodic table, I hope you're getting the pattern. It has 3 protons. It has an atomic number Z equal to 3. Let's have a look at that on our picture of lithium. In this diagram, in this part, you can see that lithium has a 3. That 3 is the atomic number. So what we recognize now is that on the periodic table, let's have a look at a periodic table quickly. I want to just pull up one that's not so fancy. Okay, here we are. We've pulled up a periodic table. Just have a look. It's very small, but we can pick it up. I want to show you a trend. Hydrogen here has a 1 next to it. That's the first one on the periodic table. If we go all the way across, what you'll see is helium has a 2. That's the atomic number. And the next one that we've got to do is come back here. We get a 3 over there for lithium, then a 4, then a 5, then a 6, and so on, and so on, until we've got all the elements all the way up to over 102 or 103. In fact, there are far more than that. It goes up to something like 117 or 118 that we've got, which is, strangely enough, way down over here. We haven't really found that one, but we're predicting we will find it quite soon. That one over there, that will fill that last period. So what I want you to see from this diagram, very simply, is that the elements on the periodic table are arranged in order of their atomic number, their Z, that number there. So it goes from 1 all the way to the biggest one. Each time the atom is getting bigger. Okay, but now what about some of the other numbers? Well, let's have a look at those, and let's have a careful get back to where we were. Here we go. So we've mentioned that the periodic table is based on increasing number of the atomic number. But there's a second number that we need to worry about, and that's called the mass number. It has a symbol A, and this tells us the number, very important, even though it's a mass, it's a number of protons plus neutrons. Now, the reason we're saying it's a number is that the units of mass here are called atomic mass units. And what we're saying is 1 U is an atomic mass unit. A proton has an atomic mass unit of 1, and so does a neutron. So if we have 1 proton, we have 1 atomic mass unit. If we have 2 protons, we have 2 atomic mass units. 1 neutron will have 1 U. So for 1 neutron, 1 of these will 1 unit over there. Now, when we add them together, we can then represent every element in this way, this notation here, where X stands for the element, A stands for the mass number, and Z stands for the atomic number. This is very useful information, and we can do some exercise on it. So let's go and see the type of questions that you might get asked when dealing with this particular notation. And here we have an example. So what does it say? In our example, it says, write down the number of protons, the number of neutrons, and electrons for the symbol representing atom X and atom Y. So here we go. Remember, the smaller number is the atomic number. Right. The bigger number, that's Z, and that's equal to the number of protons. The bigger number is A. It's the mass number. Notice it's a whole number. That means it doesn't have any decimal or comma with it. This is the atomic number as well, which is going to tell us that this is has the same number of protons. So when we look at this information, what do you notice? This has 6 protons, this has 6 protons. So what we know is X and Y are the same element. They're atoms of the same element. Atoms of the same element. And how do we know that? Why? Because the number of protons is equal to 6 for both X and Y. Let's deal with X first of all, and then let's go on and check what we're going to do. So I'm going to write X over here, 6, and X was 614. And what we're going to say is the number of protons is equal to 6. Do we know what the number of electrons are? Well, it's an atom. Remember, all atoms are neutral. And if they're neutral, they will have the same number of protons as electrons. It's not a charged particle, it's neutral. So, therefore, X has 6 electrons. The question then asked us to find the number of neutrons. How are we going to find the number of neutrons? Well, here's the trick. We know that A, this value here, this is the mass number. And the mass number is equal to the number of protons plus the number of neutrons. So can you see how to do it? Well, we know the number of protons. We know what the number of protons and neutrons is equal to. It's 14. So what we're going to say is the number of neutrons is equal to the mass number minus the number of protons, the atomic number. So in this case, 14 minus 6 gives us 8 neutrons. Got it? Hope so. So we now recognize that we've got 8 neutrons there. Let's have a look and see what we've got here. Y has 12 as its atomic as its mass number, 6 as its atomic number, let's do the same calculation, or the same y, 6, 12, and we're going to do it. Protons, definitely equal to 6. Number of electrons has to be the same number as the number of protons for an atom. We're not told that it's not an atom. Number of neutrons is equal to the atomic number minus the, sorry, not the atomic number, the mass number minus the atomic number. This was 12 minus 6. And look at that. We've got a different number of neutrons. This one has 8 neutrons. This one has 6 neutrons. Let's move on. What does it say? Identify the element in which you will find these atoms. So the question tells us they belong to the same element. How are we going to find which element it is? Well, we know there's 6 protons. We know it's got an atomic mass, or atomic number of 6 protons. Number 6 on the periodic table. Got it. So quickly, let's just look at what is number 6 on the periodic table, and maybe you'll even know it. There you go. Number 6 is carbon. So what we'll have to do is we'll have to look at our periodic table, recognize it's number 6, and we can then write down in our question the answer. To number B, well, why would we say it's the atom that this comes from? Well, let's extend it. We can say number B here, 6 protons means that it must be carbon. So, although all carbon atoms have 6 protons, they have different mass. Very important. Let me say it again. All carbon atoms, all of the atoms in this carbon, they have the same number of protons. It's the number of protons that gives carbon its particular characteristic. But they can have different masses. And the word that we give for atoms that have different masses, different number of neutrons, is the word isotope. And here we go. This is what we're saying. When things have different number of masses, different mass, they're called isotopes. Isotopes of an element have the same number of protons, but they have different number of neutrons. So please be aware of that. Different isotopes. Now, there is something that's important here. The carbon we can represent then. If we want to talk about a specific isotope of carbon, the one that has got a mass number of 14, we would call carbon 14. So we write down the element and we write down the atomic mass number. So we'd be able to say that's carbon 14. We can do it in words as well. We can say carbon 12. What do we mean when we say carbon 12? We're saying it's the isotope of carbon that has a mass of 12. All carbon has 6 protons. This is telling us we're dealing with those atoms that have 6 neutrons. This one is telling us we're dealing with carbon that doesn't just have 6 protons, it has 6 protons and 8 neutrons. Now, that might give us some problems. Can you think what they might be? Well, that means that we're not sure of the actual mass of a carbon atom. Carbon atoms have different masses. It's like you sitting in a class. You might all be in grade 10, but sure as anything, doesn't matter how well you're doing at science, you'll all have different masses. You don't all have the same mass because you're sitting in a particular class. No, the carbon atoms also have different masses. So what we'll need to do is we need to get an average mass. We call this the relative atomic mass of carbon. And here, this is our definition for the relative atomic mass of carbon. We say the relative is the average mass of all the naturally occurring isotopes of that element. The units for for relative atomic mass are the atomic mass units. So that's quite encouraging, because what we can say is that, for example, that the mass of carbon-14 atoms, the mass of carbon-14 is 14 atomic mass units. The mass of carbon-12 atoms is going to be 12 atomic mass units. What we're going to need to do is to try and get an average of those. Now, to get an average of those, we can't just add them up, because we need to recognize that in some cases, some elements, there are different numbers of things that have a mass of 12, and there's a different number of things that has a mass of 14. We call this the percentage of each isotope. So in a sample of 100 grams, we might have a certain percentage being carbon-12. In carbon's case, it's very high. It might be as much as 90-odd%, or 98%, if I remember correctly. The other bits, 2 and 3% left over, that will be attributed to other isotopes. Now, the good news is that, generally speaking, the distribution of isotopes has remained fairly stable. So this gives us a way that we can calculate the relative atomic mass of any substance, any element. So let's go and see how we do it. We're given this information. We're told that if a sample contains 69% of copper-63, remember what that means? It means it has an atomic mass of 63 and 31% of copper-65. Calculate the relative atomic mass, that's the average mass of an atom of that sample. So here we're looking at averages, and we're going to say, well, let's start. We know that we've got copper, Cu for copper, 63. Now, how much will one copper-63 atom, what would the mass be in atomic mass units? Well, in atomic mass units, what we're going to do is we're going to write down the mass. Here we go, atomic mass units. It's going to be 63 atomic mass units. Now, do all of the atoms in the sample have a mass of 63 atomic mass units? No, it's only 69% of them. So let's multiply this by 69 over 100. Okay, but that's 69%. 69 over 100. We'll get the answer to that. Let's pull up the calculator. We're going to say 63 times 69 divided by 100, and we get an answer of 43,47. So if we write that down, 43,47, and that's in atomic mass units. There we go. Now, what about the other copper? The other sample of copper was copper 65, not 63, 65. So it has an atomic mass unit of 65. It has a different percentage. This percentage, just change pen so we can see it's different, it's 31%. So it's 31 over 100. And if we multiply those out, get our calculator, we're going to say 65 multiplied by 31, or 65 multiplied by 31 divided by 100 equals 20,15. 20,15. So the answer here, 20,15 atomic mass units. So what we need to recognize is that there's no way that a single copper atom, that's copper 65, can be 20. No, this is the average within a percentage. So in a 100-gram sample, 20 of them would have, or let's say 20,15 grams would be of this substance, and 43,46 would be of that. What we've got to do to find the average mass now is to add those things together. So let's use our calculator again, and we've got to do that, we're going to say 20,15 plus 43.47, and that gives us an answer of 63,62. 63,62. Check your answer. That's it, 63,62, and we're all cool with that. So here, what I want you to see is that's the average mass of the contribution. This is the part that the 65 is contributing. This is the part that the 63 isotope is introducing. And what you can see is it's slightly more than 63 because there's the majority of them. Almost 70% are 63. A smaller number are a little bit bigger. So that's why there's now a decimal comma. And this is the relative atomic mass. It's the average of all the isotopes. And so if you go and look at the periodic table, and we slip down to our periodic table right down at the bottom, what you'll notice, let's pick one, and let's see if we can pull it up. What you'll see over here, there's a number at the bottom that says 63,5. In the copper region here, they've included other isotopes to give us a value. But you can see it's rounded off to that number, but it has a decimal comma. If we look at any other substance, you'll see that they're not whole numbers. These are relative atomic masses. Okay, so what we've done so far in today's lesson is we've looked at the fact that elements or matter must have particles below it. We've looked at starting with elements. We recognized that the atom is the building block of matter, and we've taken a look at some models of matter, of the atom, and we've focused on the nucleus. But remember, the nucleus isn't everything. There are also a layer of electrons around it. Now we're going to go to a short break. After the break, we'll be back to look at some more detail about what's happening outside the nucleus. We're going to separate from physics, which has generally focused on nuclear physics, is on the nucleus, where chemistry has focused on what's happening to the electrons. We'll be with you in a few minutes. Bye for now. Hi people, welcome back. Now remember what we've been doing. We've been looking at how matter has a microscopic view. We've been looking at the models of matter, and we started with the elements. Recognize all elements are made up of atoms, and there have been different pictures that people have drawn of the atom. And we've gone through models of the atom, and we're looking at what we think is happening in the atom today. We've looked at the nucleus. We're now going to look at what's happening to the electrons. The person that we're going to talk about is Niels Bohr. He had the idea that Rutherford's model that had the electrons just circling the nucleus in any haphazard fashion, he said, no, guys, there's some more structure, there's some more order to the arrangement of the electrons. So we have with us today what is known as the Bohr model of the atom. And the focus here is not on the nucleus. Let me illustrate this to you and say to you, there's the nucleus. And it's very small, it's at the center, and very far away. Although this doesn't look very far away, he said there are electrons that are moving in shells, like an onion. This is the first shell that's close to the nucleus. Then there's a second shell, and then there's a third shell that's further apart. Now, what's interesting to notice is that on the scale between the nucleus and the first shell, even in Rutherford's model, there was a huge difference. There's a lot of empty space. And the way you can picture this is if you imagined that you had a pea, a little pea, a green pea or a marble, and you place that on the middle of a soccer field, at the center of the soccer field, then the closest electron relatively to that size of the marble. If we made the nucleus as big as the marble, then the closest electron would be in the stands, would be outside of the field, would be at least 80 or 90 meters away from the center. So there's a lot of space. What Bohr said is, like at a soccer match, not everyone sits the same distance away from the center, but people some sit closer, some sit further, and some sit further still. What he called these layers, he called them energy levels. And he did some calculations, all based on a mathematical principle or a model, where he said, look, in this energy level, it's of such a nature that it can only contain 2 electrons. So in the first energy level, we can only have 2 electrons. So in the first energy level, we've got 2 electrons. But you'll notice in the next energy level, which these are all electrons, they're all electrons and they're putting over there, there are 8 electrons. So this is known as the second energy level. So second energy level, and we have 8 electrons. And similarly, in the third energy level, there were also 8 electrons. So he had this idea of energy levels, third energy level, and there were also 8 electrons. The inside ones in this sort of atom here, he called these, or they've become called, the core electrons. These ones are known as core. The outer energy level, the one that's at the outside, the last one that's full, that's got an electron in it, this one is given a special name, and it's very important in chemistry. This is known as the valence shell. And these are known as valence electrons. So we've got core electrons and we've got valence electrons. The ones outside, far away from the nucleus, those ones are known as the valence electrons. The ones on the inside, closer to the nucleus, but not right on top of the nucleus, those are known as the core electrons. So what we've got to remember from Bohr's model is 2, 8, and 8. Now, there's an interesting idea. How are we going to remember it? Well, guess what? Let's look at the periodic table, and we can start to recognize some things here. So I'm just going to pull up the periodic table again and have a look here. What do you notice about the number of elements in this first period? First period, period 1, has hydrogen, and if we move the line across there, there we get helium. So what have we got? We've got how many elements? We've got 2 elements. 2 elements. Remember, this hydrogen has 1 proton, 1 electron, 1 proton, and 1 electron. And helium, we're told, has 2, so it has 2 protons, 2, and 2 electrons. So there are 2 electrons, 2 elements in the first period. Have a look at the second period. 1, 2, 3, 4, 5, 6, 7, 8. Ah, that's an interesting pattern. Can you start to see? Can you guess what's happening? First period, first energy level. Second period, second energy level. What about the third period? Well, here we go. Let's check it. Remember, third period, we've got 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons and 8 electrons in the third energy level. So it looks to me like the energy level corresponds, or the number of electrons in the energy level is the same or is linked to the period number, the number of elements in the period. So if you look at the period and you look at the number of electrons, you will be okay for the first 3 periods. There are some modifications on this, but it's a useful thing to start looking at the model and looking at the periodic table. We're going to do a lot of that. flipping back between the periodic table and the model. But I think it's now time for us to see if we can draw some specific elements, the Bohr model, some specific atoms from particular elements. So let's have a look at it and let's see. It says to us in our example, draw Bohr diagrams to show how electrons are arranged in the atoms of each of the following elements. So what have we got? We've got aluminium. So how are we going to find out how many electrons there are in aluminium? So what we're going to have to do is go to periodic table, and we're going to have a look at aluminium. There it is, aluminium, Al for aluminium, number 13 on the periodic table. So what does that tell us? Atomic number 13, number of protons 13, number of electrons, atom must be neutral, 13. Okay, so what we need to recognize, also, just let's check it out, it's in period 3. So that means it should have 3 energy levels. That was period 3, so we're going to predict it has 3 energy levels. Let's go and have a look and pick it up over here, and we'll draw the diagram. So let's do aluminium first, and then we can come and sort it out with the others. So we're going to draw the nucleus, first of all, number A. I'd like to draw this in white. So we're going to draw the nucleus as that, and we can even, you can either draw it as a dot, or you can draw it as a circle and put 13 plus, and there will be neutrons in it. I prefer to just have a dot. So let's go back and just put the dot there, recognizing that that dot represents the nucleus. Then what we're going to do is we're going to have some circles. I'm going to draw them freehand, energy levels. So remember, it's 13 electrons that we're needing, and we're going to make the electrons green. They don't really have a color, but how many can go into the first energy level? Well, only 2. And we're going to put 1 over there, and we're going to put them next to each other just for the sake of pairing them. People like to be in pairs. Electrons like to be in pairs. We put them in pair like that. Now, what about that? So that we've got 13 to go. Remember, that's where we started. Aluminium has an atomic number of 13, and we're not too worried about its mass number. The Z equals 13. The number of protons is equal to 13. The number of protons is equal to 13, and that means the number of electrons is also equal to 13. So we've got 2 of those, 11 to go. How are we going to do it? Let's add a second energy level. Second energy level. Now, how many can the second energy level take? Well, it can take 8. Remember, 2, 8, 8. So let's put the next ones in. Put them in pairs. That's 2, 4, 6, and 8. Where's the next one going to be? Third energy level. So how many have we got all together? We've got 8 plus 2, that's 10. Very important, 10. It's one of the magic numbers. We're going to mention magic numbers in a little later. So what have we got here? The third energy level. We've got 10 so far. We need to get 3 more. So what are we going to do? Let's put them 2 in a pair and 1 on its own, because that kind of seems the way it should be. And there's the Bohr model of aluminium. I want you to just to notice something, that I've put 2 in a pair. This is the valence shell. Put 2 in a pair and 1 on its own. Let's have a look at the periodic table, because I think there's an important thing to notice here. So on the periodic table, there's aluminium. It's in group 13. These are group 1, 2. We're not really too worried about these transition ones. But what you notice here is there are 2 together, and here we've got, or 2 together over there, and 1 on its own. So that looks like the pairing. They pair together, and that's 1 on its own. So the number of electrons is also seems to be, this one is 3 in the last shell, the valence shell. 1, 2, 3. So the group number is telling us the number of valence electrons. Very important principle. And I want to write that down so that you can remember it. So let's just go back to the diagram so we can see that. We're going to say here, take note that the group number or the column number, the group number is 13 here. We'd have to subtract 10 or go to a different numbering system, but it's the third group on the list is equal to the number of valence electrons, in the valence shell. Okay, so have a look at that. Understand where I'm saying it's not the real group number, and we've explained that, I hope. What about the next one? Phosphorus. Phosphorus is another element. Let's go to the periodic table and let's see where we are. Here's phosphorus, number 15. Phosphorus, P15, relative atomic mass 31,0, and it's got another number over there, which we'll deal with a little later, electronegativity number. But P, notice it's in group 15, also called 5. It's the fifth one along, 1, 2, 3, 4, 5, so it's the fifth column. Let's see if we can predict. It's in also in period 3, so we're going to predict it's going to look very similar to aluminium. It's also going to have 3 energy levels, but it's going to have 5 in the last shell. So let's write it down and let's see if we're right. And that's exactly what we're going to do here. Let's write phosphorus in and get it done. So phosphorus, 15 protons, 15 protons means it is 15 electrons. And if that's the case, then let's draw the Bohr diagram there. 1 level, 2 levels, 3 levels. We're going to put the electrons in to count to 15. Remember, when the second one was full, that's 10, so it's quite easy to remember. You can see we can go a bit faster. So 2 in the first, 8 in the second, that gives us 10. Now we've got to get 5 more. So 2 together to start with. Then we're going to go 1. We need how many more? 15. We need to get to 15. 1, 2, 3. How many have we got now? That's it. There we've got it. 10 plus 2 plus 3. So that gives us 15. Notice that these ones aren't paired. I haven't paired them. I've kept them separate. And that's a particular rule that we'll come and establish a little later in a newer model of the arrangement of electrons. So we've done phosphorus. Let's do carbon and have a look at the periodic table again. There we go. Carbon, we know, is number 6 from earlier on. So it's got 6 electrons. Notice it's in period 2, and it's the 4th column along. So 4th column, and we're going to expect 4 valence electrons. Let's see if we're right. Count it up. Carbon has an atomic number of 6. That means it has 6 protons, and it has 6 electrons. So what does that mean? First energy level, going to have 2 in them. And it's just a simple counting mechanism. I hope you can see it. I'm sure you can. This is not difficult. Even younger grades can do this quite well. Let's see. We've got 4 left. We're going to pair the first 2, and then we're going to put the other 2 separate. And there we go. We've got 4 valence electrons, 2 inside, and notice that carbon was in the 4th column. So carbon, it's the 4th column along, 4th column, 4th column, and it has 4 valence electrons. Valence electrons. Got it? Right. Hope that's clear. Now what we need to have a look at is a modern view, not move on from the Bohr. Like we did with the original models, we're going to move on and look at the atomic orbital model. Atomic orbitals says, listen, Bohr didn't quite have it right. He thought about just as these strict shells. At the time, people were really starting to think about satellites orbiting the Earth, and so that the idea of an orbit, the moon going around the Earth and satellite spying and moving around the Earth in a fixed position. That was the idea. So people had started to think that, and so it translated into the model of the atom. But there were some problems with that model. When people started to do the maths, do some calculations, they found that the figures didn't work. The energies weren't quite right. Fortunately, some very clever mathematicians started to do something called quantum mechanics. And out of quantum mechanics, we've got this idea of an atomic orbital model. An atomic orbital just says, listen guys, don't restrict the electron to one particular place. It can be anywhere in an area. It can, with its energy, it's like you being given a bicycle and allowed to drive around your town. And you can map out your area that you've covered in your bicycle. You'll be able to go further than if you were walking in the same amount of time, because on a bicycle you can use up more energy. You're in a higher energy state. If you had a motorbike, you'd be able to go even further. You'd be able to travel the map more because you've got more energy. So what we're saying is the atomic orbital model is about a region in which an electron may be found around a single atom, and it's all related to energy, the energy of the atom. Now, these orbitals have different shapes, and we're going to talk about those shapes in a little while, but I want to now deal with their energy. The energy of each of the orbitals is important to understand. We also have energy levels, and we're going to talk about the energy level diagram. Now, that little diagram that I've drawn there doesn't look anything like what we've done before, certainly doesn't look like a Bohr's model, but it is very similar, and I'll show you why. Because we can number these energy levels from the bottom up, and that's what I want to do. So let's do it, and let's see how it corresponds to the periodic table as well. We're going to say this little block here represents an orbital, and we're going to say this orbital is in the first energy level. Now, this particular orbital, though it's a block, actually represents the picture of a region in space, and it's a spherical region. The electrons are allowed to move around like a bumblebee. If you had to take a photograph of that picture, a bumblebee might be moving around a flower, and most of its time is spent, some of it might be dotted around over there, most of its time is confined in a particular area. That shape is known as an S orbital. Okay? So in the first energy level, we have an S orbital, and so we say this is 1s. This energy diagram that we're drawing is also known as an Aufbau diagram, because it requires us to fill up electrons. So what we're going to do is build up, and in German we talk about building up as Aufbau, and so that's where the name comes from if you read it. So if we had one electron would have the lowest energy. Lowest energy must go into the first energy level. So just like Bohr said, the maximum of 2 can go into the first energy level. And the same thing, atomic orbital, we're saying atomic orbital, 2 electrons, lowest energy. We represent the electrons as a little arrow. So we're going to say 1 electron goes in that way. And now there's another rule that we've got to have. We say that when we put the second electron in, it doesn't have exactly the same orientation. We say it has an opposite spin, so we draw the arrow in the other way. Now, that doesn't mean too much to you. Opposite spin, what do we mean? It just means it's different. It has a different mathematical property, and we'll draw those electrons like that. The reason for that, there are mathematical calculations that say if you've got electrons together in the same region, well, what should they be doing? They should be repelling each other. But because they've got opposite spin, they don't repel each other, but they're quite happy. They're quite happy to stay in this filled energy level, filled orbital. So that's the important thing to recognize. So there's 1s. Now we'll move on. We get to the second energy level. Just to note that this is similar to the periodic table. Again, notice 1 energy, 2 atoms, either the hydrogen atom, which would have 1 electron, or the helium atom, which would have 2 electrons. Let's move on. 2s is our second energy level, also an S shape to start with. And how many electrons can go into each orbital? Maximum of 2 electrons for any orbital, whether it's an s orbital or another orbital, maximum of 2. So if we had lithium on the periodic table, remember lithium was number 3. We pointed it out earlier. So we've got to get 3 electrons. 3 electrons means 2 in the first energy level in the s orbital and 1 on its own. So that's the energy diagram for a lithium atom. What about the next one? Well, we could carry on and we could do beryllium, just add 1 more. That would be 4 electrons. Now, the principle that I want to get to is, what are these funny things here? Well, these represent a sub-level. This is known as the p sub-level. P sub-level? Well, yes, there's an s orbital and there's a p orbital. And the p orbital looks a bit like that. But there are 3 of them. The p orbitals, one is vertical, one is horizontal, and the other one, I haven't got a room for it, but it comes out towards you. So it goes y, x, and z. Okay, so 3 of them fit together, and they fit together like that. Each of these blocks here represents one of these p levels. So there are 3 p's over here, and we're going to fill them in. Now, the important thing for you, we're going to say, this is the 2p sublevel. How are we going to fill in electrons? Let's have a look here. We're going to say the next electron has obviously got to go into one of them. Now, there's a rule that says this. They can't pair up. It's called Hund's rule. You can't pair up and fill an orbital if there's another orbital in that sublevel filled. So if you see the word Hund, then it means that you mustn't put the next electron over here. The next electron must go there. And the next one must go there. The sublevel must be half full. All of them must have 1 electron, because it's not fair. They've got to be evenly distributed. So there we've got 3 electrons in the sublevel. Now, what about the next one? The next one, next electron, is going to go over there. Now it will start to fill up. The reason that we pair electrons with opposite spin, that rule is called Pauli exclusion principle. Pauli and Hund. Those are 2 names that you might read in your textbook, and sometimes you might get asked a question about Hund and Pauli, and that's what it means. The most important thing, though, is for you to be able to complete an energy level diagram. So if we go to the next one, we'd have 3s, and then it repeats itself, 3p and 4s. Right, now I'm not going to fill the rest of this in. There's an exercise that we're going to try. Have a look at this. Here we go. What does it say? It says, draw an energy level diagram to show how electrons arrange in the atoms of sodium. So, do you think you can do it? Here's the rough sketch of the energy level diagram. Sodium, remember, has a symbol Na. It has an atomic number of 11. That's its atomic number. How about seeing if you can fill in this energy level diagram on your own? In the meantime, we're going to a short break, and I'll check the answer straight after the break. Hi guys, welcome back. How did you manage on that energy level diagram? Well, let's see how we do. It's not that difficult, but it is really interesting. So here we go. We're going to fill in electrons. Remember, sodium, Na, has 11 electrons. First 2 electrons in the first energy level, 1s. Second 2 electrons in the 2s. The next electrons, we've done 4 in total. Remember, second energy level has a total of 10. Those are your core electrons. So we're going to put them in one at a time. Practice putting them in according to Hund's rule. Individually first, then pairing them. Now we've got 10 electrons. Where's the 11th electron going to go? That's right, it's in the third energy level, s orbital. Okay, so there we've got it. That's the energy level diagram of sodium. But please notice something, that if we look at the periodic table, and we'll just pull that up quickly and find where the periodic table's gone to. There we go. Have a look where sodium is. It's in the, there it is. Over there, that's sodium. It's the third period, and it's in the first group. That's where sodium is. It's third and 1. And I hope you can see that that's exactly what we've got over here. If we look at it, it corresponds exactly. Third, and it's got 1 electron. Now, there's a shorthand notation that we can use that's called electron configuration, because it is quite painful having to draw this energy level diagram all the time. So what we're going to do is we're going to do a shorthand notation called the electron configuration. And here, this is how we do it. We say, let's draw it 1s. How many electrons are in the 1s? There are 2. There are 2 arrows, so we're going to do 2. 1s2. Then what about the second energy level? There are in the second energy level, there's an s orbital, and there are 2 electrons there. And then we find there's a 2p, and there's 2, 4, 6 electrons there. So we're going to go 2p6. And then the last energy level, 3s, there we go, 1 electron. So what's it going to be? 3s1. So the electron configuration of sodium is 1s2, 2s2, 2p6, 3s1. Have you got it? I hope you've got it. Please make sure that you check yourselves back to the periodic table, because it's really important that you do that. Let's just make sure that we've got something sorted out here with the periodic table that I want to just point out to you. Just very quickly, I want you to notice that on the periodic table, this group here, these 2 groups, group 1 and 2, those are known as the S block, because all of these elements have electrons in an S energy level. All of these elements are in a P block. Now, immediately you're saying, but what about the others? Well, you don't really have to worry about them, but in terms of people that are studying further than high school, this is known as D block, and this is known as F block, and we won't go into any more of that. But there are other blocks and there are other orbitals that we don't deal with at school, but we're going to focus on the S and the P, and I hope you can see you've got the S block and the P block, and you can check yourself. Get the row and the group number, and you'll be perfectly okay. Right, let's see if you can do it now. And here's a little twist. Here's an example for us to go through. So get your periodic table in front of you and make sure that we can write down the electron configuration of the following. The first one is hydrogen. Now, I'm going to tell you, and I'm sure you've got it already, that hydrogen has an atomic number of 1, and in fact, it has a mass number of 1 as well. Most isotopes of hydrogen are 1, 1. So what does that tell us? It tells us that when we come to draw the electron configuration, hydrogen is an electron is in the first energy level, it's in an s orbital, and there's 1 of them. So the electron configuration of hydrogen is 1s1. Got it? Hope so. I want you to notice something here when we drew sodium, because before we go to the next example, what I want you to notice is that for sodium, it had 1 lone electron over here in its valence shell. But what scientists and chemists found out was when when elements had 1 electron in its valence shell, it wasn't very stable. It's very reactive. It's very reactive. It wants to get rid of that 1. What it would prefer to have, the atom would prefer to have a complete energy level. Can you see? This 1s is full, the first energy level's full, the second energy level, this one's got 2 in it, this one's got 8 in it. They're happy, they're full. Even if we got 8 in the third, it would be happy, it would be stable. But, so what that means is that sometimes, and that's what we're going to look at in this example, fluorine can change from being fluorine atom to fluoride ion. Fluoride ion means it's got it's either lost an electron or it's gained an electron. Let's have a look at what's happening. We're going to, when we're given a question like this, let's start by looking at fluorine atom. So the fluorine atom, first of all. We go to the periodic table. See where fluorine is? It's over there. It's over there. It's in group 17. Group 18 is known as the noble gases. Group 18, these are the noble gases. They are noble. They are unreactive, and they have a complete energy level. Fluorine wants to get to be like a noble gas, so it's got to have an extra electron. If it can gain an electron, it's going to be negatively charged, and it's going to form what we know as an ion. So there we go. That's what we want to draw. So fluorine has an atomic number of 9, and so we're going to draw the electron configuration for 9 electrons plus 1. Plus 1 because it's going to be complete. It's going to be like a noble gas. So 9 electrons, that will give us 10 electrons. What do you think it's going to be? Here we go. 1s2, 2s2, 2p, 6. 2, 4, and 6 gives us 10. That's it. 9 plus 1, so the fluoride ion would be F minus because it's got one more electron. It's still got 9 protons, but it's now got the number of electrons is equal to 10. So that's why there's a minus over there. That's why it's called a fluoride ion. Now what about calcium? Calcium is number 20 on the periodic table. So let's have a look quickly at number 20. It's 20 electrons. Calcium atom, 20. Now notice something here, that if we are to distribute for calcium atom, 1s2, 2s2, 2p6. That gives us 10, 3s2, 3p6, 4s2. Now that was 10 over there as well. Sorry, that's another 8, so that gives us 20. We've got it right. Up to there is 10 plus another 10, you get your 20. So where does calcium sit on the periodic table? Let's just flick back to the periodic table and see calcium is sitting over here. I just need to use an eraser so you can see it. There's calcium. It's in group 2, and it wants to be like this substance here, number 18. It wants to be like argon. What's it going to do? It wants to have the same number of electrons as argon. The moment it's got 20 because it's the atom, what's it going to do? It's going to have to get to 18 to have a filled energy level. Can't just sit with a 4s2. No, that's not good enough. It has to be completely filled. It has to be stable like a noble gas. So what's it going to do? It's going to lose those last 2. And so what we find is that the calcium atom has that as its an electron configuration, but the calcium ion is going to lose 2 electrons. So it's going to not just be calcium 20, but it's going to be calcium 22 plus 1s2, 2s2, 2p6, 3s2, 3p6, and no 4s2. It's lost those 2. So have a look now what the arrangement is. It's got 20 protons. It's got 18 electrons. Can you see there are more protons than electrons? So that means that it has an overall charge of +2. Whereas fluoride, where we looked at it, had 9 protons and 10 electrons. That's why overall it had a negative charge. Well, we've rushed that a little bit, but I think it's important that you start to get the idea that stable atoms are those that are in group 18 or have an electron configuration that is complete. The energy levels are filled, like the noble gases. Now, that brings us to a point. Well, what do we know about these things called the noble gas? Well, we've just spoken about atoms, but let's talk a little bit about atoms as they get together with other substances. And that's our last point for today. We're going to talk about noble gases. Noble gases are unreactive. So even if I have some noble gas, some helium or some argon in a tube, it will be atoms floating around. Noble gases are made of atoms that don't link together. They don't combine. Put the heading there, combining atoms. Remember, they are unreactive. There is no bonding. There's no joining together. There's no bonding. They are atoms. So these atoms, we sometimes say that these atoms just exist on their own. They exist as particles that will float around as gases. Now, in some ways, we also use, and it's sometimes confusing, we say molecules of noble gases, because they aren't joined to anything, and it's kind of they molecules. That's not really correct. They really are atoms that are free and sorting around. When we look at the non-metals, what we can find in the simplest form, two atoms can join together to form a molecule. So here is the building block, two forming together. But it doesn't just have to be two. We get two forming together, hydrogen and hydrogen join together to form a hydrogen molecule. There are 7 diatomic, 2 atoms per molecule, 7 of them. I want to list them for you. H2, F2, Cl2, Br2, and I2, and then At2. Now, those are all the diatomic molecules, 2 atoms per molecule. Doesn't mean that you have to only have 2, but because if we look at something like sulfur, it has 8, and phosphorus has can have 4. And so there are non-metals that have more than 1 atom in the molecule. And in fact, if we look at something like carbon, we can get a whole range of atoms joining together. They've bonded together to form a very big structure, which we know as a network. There are 2 forms of that, graphite, or 3 forms, graphite, buckyball, and diamond. These are all giant molecules of carbon. There are other substances that have similar ideas. Similar to that, we go to the metals. In a metal, like our copper, we haven't just got 1 atom floating around, but they're joined together. They join together in a special structure. We call it a metallic lattice. It's joined together, 1 atom linking to the other. We're not going into the detail, but what I want you to get the idea is that atoms fit together to build up from the very small, the microscopic, to a bigger structure. And so the next thing after atoms, metals at least, we get to compounds. And very quickly, I want to just mention that in compounds, we can get different structures. We can get things like the little crystals that we had, that I showed you earlier. Those are known as ionic structures. We can get the ice, which is almost melted at the end of this filming of this lesson. That's a molecular structure sticking together. And so what we recognize, we can get ionic, and we can get molecules that form together. To form compounds, they join together. We can represent this combination in different ways. And that's the last thing I want to do, is just to mention to you, for compounds, we can write formulas. So we can write NaCl or H2O, and it tells us which atoms are joining together. We can also draw little diagrams to show, for example, that that's an oxygen and that's a hydrogen, and that's a stick and ball diagram. And we can also do something called a space-filling diagram, where we draw that and that and that. These are all ways of representing the particles that matter is made up of. Now, I really hope that you've got the overall picture, from the very small to the giant, and recognize that it's all because of our understanding of the atomic structure that we can understand a little bit more about the microscopic view of matter. I hope you've enjoyed this session, and do practice all of those important examples that we've done, and I hope to see you soon.